Welcome back, everyone. This is Professor Herring. In this video, we're going to continue our discussion of chemical reactions. Specifically, we're going to learn about oxidation and reduction, also called redox. Let's begin. Redox reactions we've already briefly mentioned as one of the subcategories of reaction types. And redox reactions involve transferring electrons from one reactant to another reactant. There's two terms that you need to be familiar with. One is oxidation, and oxidation is defined as the loss of electrons. In contrast to oxidation, we have reduction, where reduction is the gain of electrons. We also need to be able to talk about the substances that are performing the oxidation or reduction. And the oxidizing agent is the substance that causes oxidation. Think of it here's one way to think of it. An agent does something. It performs an action. So an oxidizing agent is an agent that's oxidizing something else. Whereas a reducing agent is an agent that's reducing something else. And notice that the oxidizing agent gets reduced and the reducing agent gets oxidized. So this we can summarize in the following diagram. The reducing agent gains electrons. It's causing the reduction to occur for substance B. And so the reducing agent donates its electrons to the oxidizing agent. The oxidizing agent oxidizes the reducing agent, and therefore the oxidizing agent has been reduced and the reducing agent has been oxidized. And so we see that these are essentially two halves of the same coin. You cannot have oxidation and reduction without the other. And so this term, redox, comes from reduction and oxidation put together into one word and simplified. And there's some mnemonics that you can use that will help you to remember these different processes. One is oil rig. And so taken apart, we can write that as oxidation is loss, reduction is gain. And of course, it's implied that these are both talking of electrons. Another way to say this that you might have heard is Leo, the lion, goes grr, and that's lose electrons is oxidation, and gain of electrons is reduction. Either of these are essentially saying the same thing, but there's just different mnemonics. My recommendation is that if you can come up with your own, that will make it more memorable. So there's some rules for determining what are called oxidation states or oxidation numbers. And these you can find in the ebook in one of the supplemental pages. There's a stop sign that indicates this information, or where to find this information, rather. The first, and generally speaking, these 5 rules are given in order of priority. So the oxidation state of an atom that's in elemental form is 0. Now, what do we mean for an atom in elemental form? We're talking about something where we have one type of atom and it exists in its common form in nature. So that would be chlorine, Cl2, oxygen, O2. You could have phosphorus, carbon, sulfur, any element. You can add to this, these are just examples of nonmetals, but you can add to it any metal, so long as it's elemental. Lithium, calcium solid, magnesium solid, etc. Notice that these are not ions. We'll get to that in a minute. So for all of these elements, the oxidation number or oxidation state is 0. If we are talking about an ion, and it's a monoatomic ion, then the oxidation number is equal to its charge. So for example, if we can look at chloride, it has an oxidation number of -1, equal to its charge. Iron 3 plus would have an oxidation number of +3. The third rule is that there's some elements are going to have common oxidation numbers, and that we can use those common oxidation numbers as a reference for determining other oxidation numbers within a compound. So notice in these first two cases, these are elemental. Whereas in this case now we're talking about if we have a compound. So for example, the group 1A metals, such as sodium, lithium, potassium, cesium, those are all within a compound are going to have an oxidation number of +1. The group 2 metals, the alkaline earth metals, are going to have an oxidation number of +2. Hydrogen usually is going to have an oxidation number of +1, with a couple exceptions. If you have what's called a hydride, and that's a metal bound to oxygen or hydrogen, then that's going to have an oxidation number of -1. Fluorine always has an oxidation number of -1. Oxygen usually has an oxidation number of -2. And so you'll notice that in these cases where we're talking about compounds, the oxidation number usually is what the charge would be. If it were an ion. And we'll talk about the exceptions to that in just a moment. So for oxygen, some exceptions are peroxides or superoxides. And peroxides, that's a case, the most common one is hydrogen peroxide. Or superoxides, that's where we might have something that is, or another peroxide would be NaO. The halogens, chlorine, bromine, and iodine, are usually -1. And so within these rules, notice that some have no exceptions. In these cases where we're usually, the exceptions will be based on group 1 and group 2, fluorine. So in other words, these rules that are absolute take priority. And so they can force oxygen or the halogens or hydrogen to take on non-ideal oxidation or non-normal oxidation numbers. So to help us determine that, we have to realize that the sum of the oxidation numbers equals the overall charge. So for hydroxide, hydrogen is +1, oxygen is -2, the sum is -1. For O2F2, fluorine always is -1, since the sum must be equal to 0. There's 2 fluorines and 2 oxygens. That means that the oxygens would have to cancel out the fluorines. And so each oxygen would be a +1. So again, oxygen is usually -2. However, when combined with fluorine, it can change. And this brings us to the 5th rule here, and that's when we have shared electrons between nonmetals, the more electronegative element is going to get the negative oxidation number. Let's talk now about the difference between oxidation number and formal charge, because it turns out that the oxidation number and formal charge are very similar in how we would determine them. So neither concepts are the real charge of the element, but they each have their own purpose. For formal charge, it tells us the charge if the bonds were to be nonpolar covalent. Whereas oxidation state would indicate what would the charge be if the bonds were ionic. And for oxidation numbers or oxidation states, this is important because we're interested in looking at where are the electrons flowing. So for example, if we take carbon dioxide. The formal charge of oxygen and the oxidation number or oxidation state of oxygen we can calculate. And so formal charge is calculated by the valence electrons minus the lone pair electrons minus half the electrons in bonds. Whereas the oxidation number is calculated by the valence electrons minus the lone pair electrons minus the number of electrons in minus all of the electrons in bonds if it's more electronegative. So for example, oxygen has 6 valence electrons. There are 4 lone pair electrons. And then there's 4 electrons in the bonds here. And so it gets half of those, which is 2. And that would give us a formal charge of 0. However, if we determine the oxidation number for oxygen, it's going to be the valence electrons, which is 6, minus those 4 electrons in lone pairs, and it gets all of the electrons within the bonds because it's the more electronegative element. That would give it an oxidation number of -2 here. So let's practice now. But in reality, so as I said, these don't actually indicate the charge. In reality, we know that there's a partial charge. There's a slight dipole moment or bond dipole, and there's a partial negative charge on each of the oxygens and a partial positive charge on the carbon. So let's practice here with an oxidation number. We want to know what's the oxidation number of phosphorus in the compound given below. So let's start out by writing out, organizing our information. And we know that sodium is an alkali metal. It's always going to have a +1 oxidation number. Generally speaking, hydrogen is going to have a +1 oxidation number as well. The exceptions to that, remember, are if we had a metal hydride, so just the metal with hydrogen. In that case, it's going to be -1. Or if we, excuse me, really that's actually the only case, is metal hydrides are going to be give it a -1. If it's combined, it could be a metal hydride singularly like this, or it could be a metal hydride like that. And so calcium would have +2, and there would be -1 for each hydrogen there. The oxygen is more electronegative than phosphorus. So when we look at these, phosphorus, we would probably expect it to have -3, oxygen a -2. However, when we evaluate nonmetals that are bound to each other, we give the more electronegative element the negative charge. And so oxygen gets its -2 charge. And so phosphorus is unknown. We know that the sum of the oxidation numbers must be 0. And so for sodium, there are 2 sodium atoms, each at +1. There's 1 hydrogen atom at +1. There are 4 oxygen atoms at -2. And then there's 1 phosphorus at some unknown value, and that's going to be equal to 0. When we simplify this, we get 2 + 1 - 8 + x = 0. And so if we then solve for x, we see that x is equal to +5. So we've talked already about single displacement being redox reactions. But now we're a little bit better prepared to understand what's going on here. So if we want to write out the reaction between zinc and copper sulfate, what we can see is that zinc is starting as a solid, and it's ending up as an aqueous solution with zinc with the sulfate ion. So if we write out the complete ionic equation, we write our zinc metal, we dissociate the copper sulfate. Again, this is because it's a strong electrolyte. We dissociate the zinc sulfate, also because it's a strong electrolyte, and then we have copper. Now we can eliminate, or write our net ionic equation by eliminating our spectator ions, which is sulfate. So we're left with zinc metal plus copper ions yields zinc ions and copper metal. So what we can do next when we're dealing with redox reactions is write them out as what we call half reactions. And so if we want to ask what's being oxidized, what's the reducing agent, remember oxidation is loss of electrons. So which of these substances is losing electrons? We have zinc going to zinc 2 plus. We have copper 2 plus going to copper that's neutral. If we're losing electrons, that means it's becoming more positive. Well, zinc's becoming more positive. And another way to look at this is to think, how would I be able to balance out this equation? Because I have 0 charge on the left and plus 2 on the right, so I need to add 2 negative electrons on the right to balance out the charge. Copper, in order to balance the charge here, we need to add in 2 electrons as well. And so we can write these as our separate half reactions, where the zinc metal is being oxidized and the copper ions are being reduced. And what we see is that if we were to add these back together, the electrons would cancel out and we're left simply with our net ionic equation. Let's do another practice problem here. Go ahead and pause the video and try this on your own, and then you can resume and watch the solution. Welcome back. So shown below is a chemical reaction involving samarium, Sm. Which substance in the reaction is the oxidizing agent? Well, remember, the oxidizing agent is going to be reduced. It oxidizes the other substance. So the best way to figure this out is to determine what are the oxidation states and how are they changing. So this is our molecular equation. To write out our full ionic equation, we have samarium plus C2H4I2. And this is not going to dissociate because it's all molecular. That yields samarium 2 plus 2 iodide ions plus C2H4. Now, how did I know that it was going to be I minus as opposed to I2 with the 2 minus? Because this is an ionic compound and it always dissociates into its smallest pieces. And since iodide is not a polyatomic ion, it dissociates into the single iodide ions. So when we take a look here, we see that samarium is going from 0 to plus 2. That means that the samarium must have lost 2 electrons. And so this process is the process of oxidation. Whereas when we determine the oxidation numbers of the other elements, we can see that this compound we're losing essentially the iodine atoms. And so from the we know that this is oxidation, so then this must be undergoing reduction. Since this is undergoing reduction, it was reduced. It is the oxidizing agent. And so that means then that our C2H4I2 is our oxidizing agent. Oops, we skipped ahead too far. The last thing to talk about here is what's called the activity series. And the activity series ranks metals based on their redox stability or their potential. Notice that in all of these cases, we're writing them as oxidation half reactions. And what we see is that as we go up the scale, the ease in it's easier to oxidize. So in other words, these processes up above are favorable, and these are not favorable. We see that substances like gold and platinum and silver and copper are hard to oxidize. What that means then is that they're going to prefer to stay in their solid metallic state as opposed to becoming ions. Well, this actually aligns with our understanding that the alkaline and alkali metals and alkaline earth metals are very reactive. Whereas these metals are what we call the precious metals. This is exactly why silver and platinum and gold are used as jewelry, because they don't oxidize very easily. They are going to stay in their solid form. They're going to remain pure. Clearly, if you've ever looked at the Statue of Liberty or a copper penny, you know that oxidation can occur, and silver can tarnish. But it requires reacting with a substance on the top end of the activity series. And so as long as you keep those substances away from lithium and potassium and barium, then they're going to remain relatively safe. So that's it for this video. Thanks for watching. If you have any questions, please ask on Piazza or in office hours or recitation. See you later.